we need to start making more conscious material choices.
I set up an initiative called Make Fashion Circular.
It's a tsunami of change.
Welcome to the DIF, the Ellen MacArthur Foundation's interactive online events series that aims to inspire action and shift mindsets towards the circular economy. My name is Seb and I'll be your host for this session for the next 45 minutes. And it's my pleasure to have the chance to ask questions to our two guests. But this is an interactive session and we also want your questions, your comments, your feedback. And there's a few different ways in which you can do that for us. You can post them on the web page that you're watching this on the ThinkDiff website. There's a section on the right-hand side to post comments in there. If you've already navigated to YouTube, post your questions and comments on the YouTube page or tweet us using hashtag ThinkDiff. Now, so they say that for every design problem we've ever had, nature has already solved it, from adhesives that hold underwater to materials that are stronger per inch to steel than to the flight itself. There is a lot we can learn from natural systems and the way the living world works. And the study and application of nature's solutions is called biomimicry. And today I'm very lucky to be joined by two experts in the field of biomimicry. At least I'm dubbing them experts, no pressure, Richard and Veronika. So I'm joined by Richard MacCowan, founder of Biomimicry Innovation Lab, and Veronika Kapsali from the London School of Fashion, who are both actively designing products and applying this to real life action. So perhaps the first question has to be, what is biomimicry?
So I'll start. I'll take that one, shall I, Richard? Biomimicry essentially is a term that was the outcome of some work that was being done in the beginning of the 20th century. Biologists and physicists were started to collaborate and apply physical principles in order to explain the phenomena in biology. And that particular discipline was called biophysics. At the time, there was a young, very talented biophysicist called Otto Schmidt, who around about the 1950s was working on his doctoral thesis looking at a particular application that was inspired by his research in biophysics. And he didn't have a name, or there wasn't a term that he could use to describe what he was trying to do, which is essentially apply the knowledge that he was developing and gathering through biophysics into the technological world, into engineering. And so he coined the term biomimetics in order to describe that very thing, the application of knowledge and understanding from biophysics. But of course it didn't start there. It's a wider concept that began thousands of years ago, and I'll let Richard talk more about that.
You can take us back 1,000 years, Richard.
Yeah. Whoa.
In the beginning.
In the beginning. No, I mean, to me, biomimicry is about looking at how nature solves problems and then translating that into our man-made technologies, whether it's pure innovation or whether it's sustainable or environmental. It's as simple as that, but it's also as complex. There's so many different descriptors of biomimicry as there is for the circular economy. I think it's like 192 or counting for circular economy. And I don't know if anyone's done the research into biomimicry and biomimetics.
So we've had, it sounds like there's a bit of biology and physics. There's a bit of kind of looking at nature, observation, design. It's a very multidisciplinary, interdisciplinary concept. Is that a fair comment to make, and is that essential as well?
Oh yeah, I mean, 'cause you have to consider, so example being the Royal Society, this year been looking into circular economy and biomimicry as well. And with that, they brought chemists and material science and some product designers together. And the great thing about that is they need the industrial and product designers to speak to the chemists to come up with new biomaterials that are better than the ones we've got. And it's getting out of the silo of design and business that's very much was a peculiar problem of the 20th century, even going back to the Industrial Revolution, where we're actually just saying, right, you're good at one thing, let's focus on that. When you look at back to the great innovators, going back a few hundred years, they were influenced by multiple areas and also worked in different fields as well.
And so that's some of the science, like what is it? Maybe one of the best ways for us to start talking about what it is or help the audience get to a place where they maybe can see it a bit more is to talk about what it actually looks like, or what it looks like to start thinking in this way, and also what it looks like when you make stuff from that. And I can see that you guys have brought together almost could we call this an exhibition of biomimicry? Is that a fair term?
Yeah, we pay people £1 to come and see our exhibition. It's the cheapest we've got, but yes.
So why have you brought some of these things? I don't know where the best place to start necessarily is, but
Velcro.
Yeah.
why have we? Yeah, so Velcro is almost one of the most famous examples. If you have already heard of biomimicry, you may have heard of Velcro. What's the story there?
Okay, so Velcro was inspired by this phenomena. So what you have here is burrs. These are quite large burrs. They come in all sorts of different sizes, but these just happen to be the ones that grow near where I live. And
You've picked these burrs yourself.
I have. Well, I've picked them off my clothes. So around about the 1950s, a mountaineer called Georges de Mestral, who loved to walk his dog every day in the mountains, would come down and spend lots and lots of time taking these burrs, pulling them off his dog's fur and off his clothes. And he was curious to work out, how could these little structures be so difficult to remove from fluffy surfaces. So a simple observation under the microscope revealed these tiny little hooks that form at the tip of every spike. And those tiny hooks are what clamp onto or hook onto the fluffy surface, make it very, very difficult to pull off. So if I try and pull this off a toweling fabric which mimics the fur of an animal, it's incredibly difficult to disconnect it. And actually when you do, you get these little bits that come off that have seeds on them. And essentially that's what the burr wants to do. It's a pest. It doesn't produce any fruit or anything that an animal would want to eat. But it still needs to disperse its seeds. It doesn't flower, it doesn't grow high up, so it doesn't get blown away by the wind. So the mechanism it's developed or evolved in order to get its seeds around is by becoming an annoying pest that just letches onto your clothes.
And how do you go from that to Velcro?
So, having identified these little hooks on the tips of the burr and the fluffy surface, he thought this would be a fantastic technology to bring into the man-made sector and create structures or systems that can stick to each other without using glue and are reversible. So he collaborated with a French fabric mill that specialized in making these sorts of cloth structures. So what you have here is the cloth being woven in the XY direction, and additional loops or piles, as they're called, being introduced into the Z direction. And he felt that was a fantastic starting point. So originally they made some trials creating fabrics using this particular structure with cotton, and what they could do was they created obviously a surface that was just like the towel, but they could control the amount of loops that you'd get per square inch or square centimetre, and they could also disrupt those loops, so break them. And this is how they engineered the two surfaces. So the surface with the broken loop mimics the needle tip of the tip of the burr, and the fluffy surface imitates or replicates the furry sort of animal skin.
So the sticky bit of the Velcro has the similar like the sort of hook bits on it.
That's
I mean, no, I've never observed that about Velcro before, because you never really looked that closely at it, I suppose. I mean, I've had tied up shoes now for a year, so
yeah.
but
Congratulations, it's
thank
quite
you.
a skill.
Yes. But what you're saying is actually, if you looked really closely at your Velcro in whatever you use it, you would actually see, I don't know if you did a microscope, but you can actually see the structure.
That's right. You've got Velcro isn't one bit of material, it's a system of two materials made using the same process. However, one and the same sort of textile structure. One surface or one part of the system has got a fluffy bit, and the other part of the system, the other component, has got broken loops on there, broken bits of pile that replicate the tip. And if you look closely, you can see, you don't need a microscope. I'm getting old and I need glasses, so different glasses, so I'll be doing this. But normally you can see it quite clearly with the naked eye.
Next time you're using Velcro, look a little bit closer. What I like about that example is that, like, we've all used Velcro probably at some point, and obviously it's an extremely useful technology, for lack of a better word, it has a number of different functions. Don't sit there and think to yourself all the time, well, that was inspired by nature, but it's an incredibly useful thing that was inspired by nature. So in many ways, whether you know what biomimicry is or not, you're kind of affected by that mindset or that way of thinking. What else have we got here? Pine cones. What's the story behind pine cones?
Okay, so I studied biomimetic design, biomimetic engineering as part of my PhD many years ago now. And I was invited to study at Bath University with Julian Vincent, who was my supervisor, who headed up the biomimetic group at Bath University in mechanical engineering. So I was working in the same office as people making very interesting robots that fly and roll and do all sorts of things, inspired by nature. But my interest was to explore ways in which biomimetic design principles could be applied to textile design. Because of my background in fashion and textiles. So I was very interested in looking at the comfort, and in particular what happens in our microclimate, which is the space between the skin and the first layer of our clothing, and looking at what happens when we sweat. So moisture was a very important factor in the design of my research. So when I was at Bath, I worked with Julian Vincent, who introduced me to the notion of plant systems, plant structures that autonomously open and close or change their shape in response to moisture without requiring any additional energy input. It was literally just due to the materials and the way they were designed. So to cut a long story short, I studied the pine cone and many other systems that have similar principles, and it's very simple the way the pine cone opens and closes in response to moisture. So you can see here you've got a closed pine cone. This is a damp one, and the reason the pine cone closes in damp conditions is because in here it stores all its little seeds, just like the burr we spoke about before. This is a structure that's engineered for optimal seed dispersal. So when it's rainy and damp, if the wind blows the seeds away, the seeds will get hit by the rain and land very close to the tree itself, which is something that the tree doesn't want to happen, because then it will be in direct competition for resources with its parent. So the optimal conditions are when it's dry. So and that's why the pine cone closes up when it's damp in order to protect the seeds and lock them in to prevent them from flying away. And then when it's nice and dry, it opens up like this, allowing the wind to sort of blow through and carry the seeds as far away as possible. Now, pine cones are dead. They're not connected to the tree. And they demonstrate this opening and closing continuously for years and years and years. I mean, I've got pine cones that are 10 years old and they still open and close.
Spraying water just.
I never get bored of that trick. And you know, they completely just do this amazing function without, you know, there's nothing connected here. They're not part. No, absolutely not. You don't need a battery, for example, to replicate this function. So I studied, and drawing on my textile background, I explored ways in which I could translate the mechanism that was responsible for this opening and closing into a sort of textile technology platform, which is why that's
the idea of that being that it's useful for us to have fabrics that kind of respond to temperature as well, or water or whatever, so that, you know, they become waterproof and they can become aerated, and
yeah,
that's a smart textiles maybe.
Absolutely, but without any electronics.
Yeah.
Yeah, so the research that I was doing looking at physiological comfort, specifically next to the skin, was showing me that physiological discomfort, so when you feel icky and sticky after you've been to the gym or you've been running around and wearing too many clothes, is actually due to the moisture buildup in the microclimate rather than an increase in temperature, because you might feel that you're getting hotter, but actually before you feel uncomfortable, your skin has already started to perspire. So there's an indicator there that, you know, just before you start to feel the discomfort, your skin is already emitting
which is another
sweat.
Process in biology, right? That's,
oh,
you know,
completely.
It's keeping you cool,
yeah,
but you still feel hot because you've got clothes on over the top of it.
You've got to wear clothes. We're not quite there yet where we can walk around.
My 2 young children disagree from running around our house naked, which I'm sure they'll love me
How then, so what you're currently working on in that field is a fibre that if you, like, wearing gym clothes and you're sweating, it somehow acts a bit like the pine cone,
yeah,
and opens up a bit, or what? How does that actually? What's the actual technology there? Or the...
So what we've got here is, after I finished my PhD, there was quite a journey that happened. Obviously, the IP that we developed was interesting to the private sector. So I secured some investment and a business partner who helped me take the IP away from the university and develop it further in the private sector in our and conducting R&D. So what the first step was to create a fibre that has these characteristics. So this is InnerTech Fiber, which is the brand name that we've given our fibres. And what they do is, in damp conditions, they shrink because they are structured. Their sort of composition and design is very similar to the way the pine cone works. And instead of opening and closing, we have a shrinking mechanism that happens. And you can see, if you were to compare these two, this is the fibre length in dry conditions, and then this is how it shrinks in response to moisture. So I've just sprayed that with a few.
Just in case our audience doesn't pick up, it's a lot shorter.
Yeah, it's about 60% shorter than the original.
And you just
length.
literally, before we went on air, I was like, what are you doing, Veronika? Just spraying water all over our desk.
Yeah.
And that... yeah, now you're spraying on Richard. But yeah, and the effect of that was almost immediate. It's shrunk down 60% of the size.
Yeah.
And the benefit of that is that...
So then we've been thinking about of ways of which we can incorporate that into a textile structure. We've tried various different applications or various different approaches. Textiles are hierarchical in structure, just like biological materials, many biological materials. So you've got fibre level, and then you go up a scale and you've got yarn, and then you've got knitted and woven textiles. But what we've done, there's another class of textile called nonwoven, which is this sort of material here. So it's random fibres layered on top of each other and then glued or bonded together using all sorts of different processes. So we felt that this structure would give us the most functionality in terms of shrinking and elongating in response to moisture, because we're not restraining the fibres in the way that they would need to be restrained and twisted and processed if we were turning them into yarns. So what we have here is we were funded about 18 months ago by Innovate UK to actually develop prototypes using our fibres into non-woven materials, and we're currently at the end of that project, and we've successfully produced fabrics that alter their shape as they absorb moisture. So we have one version. So these, I'll go back. These materials are used to manage insulation. So you'd find this inside a puffer jacket, for example, inside a sleeping bag, any garment system or any garment prototype accessory that requires insulation. And the amount of insulation that particular fabric gives is directly related to the amount of air that's within the textile system. So in principle, if you've got the same amount of fibres but thinner material, then you can, or a material that can control its thickness, you can control the amount of heat that the system retains. And we proved this because we were able to create a non-woven material that could change its thickness in response to how damp the environment was. So in damp conditions, the material is thinner, therefore less insulating because you're running around and you're sweating. And when it's dry again, it sort of assumes its original position and provides extra warmth. We also have another version where the shape change is orientated in an XY dimension, and by securing and by cutting into the fabric surface, we've created tiny holes that open up in damp conditions. So you've got a fabric that becomes more porous as it absorbs moisture. So that's where we are with that.
So we've had one example kind of like from the 1950s almost being inspired, the Velcro example. Now we're talking about like actually some quite cutting edge, like that sounds like something that, you know, almost futuristic textiles that kind of respond. And it's all inspired by nature.
Yeah.
Richard, when we were just walking to the studio, you grabbed that Satsuma and you said, can I borrow this? Why did you do that?
Well, because if
You're
you think...
just hungry.
Well, I'm hungry as well. You know, you fed me yet. But one of the things is, although I couldn't find it, is a pomelo, which is a large orange. And basically, if you think about it, these fall off the trees and then they don't bruise the fruit inside. And if nobody minds me peeling it into it. Unfortunately, you can't see it because it's not quite the same as a pomelo, but the structure of basically the flesh inside, what it does is this type of material called an exotic material, and actually distributes the energy round the skin instead of actually into the fruit. And you're getting smart textiles developed in this way. BMW are now actually developing helmets for use in their factories that are a lot more lightweight, but then protect their workers a lot better. And
someone like BMW, have they been inspired by nature? Or
Yeah. So they directly worked with research teams based in Stuttgart and Freiburg. But it's back to one of the things you were mentioning. Actually, you hit the nail on the head when say we look around for ideas. So cast your mind back to school when you were doing an arts project, any project, you put together your ideas board, and you put some leaves on it or any animals. But why not just then delve a little bit deeper and see how it works? Well, there's an example I can give here, which is aquaporin. Now, obviously, I'm not going to show you. Aquaporin are the cells in plants and how they absorb moisture. And what it does is it doesn't allow anything that's not H2O through. So it's a bit like them quoting this song from Cypress Hill. So it's a membrane
Not water,
technology.
you're not allowed in.
Yeah, exactly. And now a company in Denmark has called their company Aquapor, and they're looking at various filtration technologies based in this material, so you could put them into piping anywhere where you want to stop pollutants getting through and just filtering the pure water.
Constantly looking for ways to purify water as well.
Yeah.
And that's a genuine challenge, especially today.
Well, exactly. Today, anywhere in this UK, if we've got too much water, or places that don't have enough, but then have to filter it to, maximise the the fresh water you've got out of it, or even into space applications when you're recycling water time and time again.
That's great. So that's the Satsuma. I'm slightly nervous about asking about the golf ball, but I think I have to.
I just keep this in my bag, actually. I just put it on the table. No, seriously, it's about the fact that when you start looking into biological surfaces, it's very rarely they're super smooth. When you delve down, you get the microscope out, down to the micro or nano level, and what you're finding, a bit like a golf ball. So when golf was first invented, basically the golf balls were smooth, and as they got bashed a bit more and more dimples in them, they actually flew further. So you start thinking about the fact that golf balls fly because it creates these little mini microvortices around it as it spins. So if you look into feathers, you look into fish as moving through water, anything, down to the fact when you're looking at lotus leaf and how the fact that they're collecting up particulates of dirt and water, it's down actually, there's super, they look super slippy, but they're actually super bumpy as well. It's just the way that we perceive them.
The fact that I guess an example, they haven't necessarily looked at a natural example.
Well, it's just an easier example than me say bringing in sailfish.
They've learned kind of the same thing.
Yeah.
As they've almost evolved. The golf ball has evolved much like the bird's feather.
Exactly. Yeah, and
Is that
a
too
lot.
grandiose?
Example. I mean, there's even golf drivers now inspired by dragonfly wings and the structure of where the material and actually the basically the struts are, and actually the various materials. So actually looking at light weighting and putting the energy where it needs to be and the material where it needs to be.
One of the things that I find interesting about this topic as a whole is the kind of juxtaposition between complexity and simplicity, and often the result and idea is quite simple, like it makes sense. But obviously, so the example of the fact that actually most surfaces aren't flat, they're actually much more complex than maybe they first seem, even though it's obvious, golf ball, little ball on the ground, you hit it through the air. Doesn't seem that difficult, does it? But actually, that example illustrates that there's a little bit more to it. And I know that one of the things you talk about a bit, Richard, or interested in is the kind of observation of systems, and actually taking this above like a single product lens, but actually how do processes and how can you design a system and process also inspired by nature?
Yeah, I mean, let's skip through we'll go past the penguins. I mean, ants. I love studying the ants in my garden, or occasionally come into my house. My wife wouldn't let me talking about that in public, but there's a complex systems. These animals are, very small brain, but they communicate through pheromones, trails. There's a chaos in the order. There's built-in redundancy through the swarm as well. So they work as a, complete hive mind effectively, and they problem solve. They know where the food is. Once one of them finds the food, they go to find it. They build nests. They're all working together, and it's this kind of study of you start seeing changes in complexity, self-organization, and kind of some emergent properties that you kind of unexpectedness that you don't normally get by just looking at kind of a simple processes.
So yeah, you could be walking around in your garden perhaps, or in your kitchen, see a load of ants walking around, and just think, oh, there are ants walking around. They've got quite a simple goal. They're not doing anything crazily complex. They're building a nest. They're getting food. But actually, if you watch the patterns of the way they're moving there, and you studied it, you'd see. And I guess one of the things is, what can we learn from examples like this?
Sorry to interrupt. There's computer scientists out there studying the complexity of ants and other basically swarm insects. And one of my advisory board members, a brilliant guy called Dr. Rupert Sower, and the teams he's working at both in the UK and America, they've been studying termites. Now, termites are related to cockroaches, and they're effectively blind, live, these are specifically Namibian termites, and they like living in the 80% humidity level, and they keep building, and they cooperate and compete. So some of the termites are putting down mud because they're sensing the environment inside. Some are taking away, and they're constantly doing this over and over and over again. And they're interesting. They actually build by sensing the kind of the gas levels in the termites, because what they're actually doing is they coexist with these fungus that live underground, and we're not quite sure whether the fungus are in charge or the termites. It's a bit like people who've got gluten intolerance and your stomach swells up and then you've got your gut biome making you grumpy. Who's in charge? Is it your gut biome or your head? It's an interesting question. Yeah. Or start thinking about, the microflora. So what can we learn from this? Well, think about this. They are the sensors as well as the builders. And how could you actually then develop, say, a 3D printing system that actually senses the environment and builds at the same time, instead of just taking in the programs we've put into it and it's passively part of the system? You can look into various ways of building, not just buildings vertically, but they're effectively cities. So you're looking at the flow of materials and how they're collecting it and building it as well. And they're completely changing the structure all the time. You've got the built-in redundancy of the termites in there as well. And there's a fascinating way of looking at this kind of complex society, working in tandem with this fungus to survive.
What's also interesting about these two examples that Richard has shown is the nature of the information available within the environment and the nature of the instructions. We're used to instructions being digital in computer programs, but here the sort of code is completely physical. You're looking at, you spoke about pheromones, you spoke about, in this case, the humidity and the particular sort of sensitivities of each organism. And it's a very, very interesting way of looking at the nature of information.
Yeah, and you could effectively do that. So think about, there's a lot of studies now in building physics and building modelling, and what if we could do that? We can't just walk around in our office and rearrange all the furniture just because we're feeling too hot. But it's that kind of thing, is how can we teach people designing offices to design them more effectively based on the information that we're providing, instead of them just kind of guesstimating or using computer models. So it's giving very much the humanness back as well.
Something else I sort of noticed by that example is we're quite obsessed with efficiency, but it's not overly efficient to have half the termites building up structure and half of them taking it away, but it's possibly a more effective solution.
It's building in resilience
Yeah.
into the system as well. So there's a great example of Toyota's and their supply chain. And in Japan, there was a natural disaster, and because it was a linear system, they were looking at the most effective way to getting all their parts to the factories. The natural disaster caused that to knock out, but if they built in a less efficient but more resilient system with different distribution nodes, they would actually kept the supply chain going, building the cars, instead of just trying to optimize all the time and make this maximum efficiency, because you rarely find that in the natural world.
When you look at the natural world, it's not often about perfect, efficient supply chains, one source in, and because those things wouldn't survive over the long term, which is an interesting proxy for things.
It's even looking at our human body. I mean, you were talking about sweating. We're not an efficient system. There was an article in Nature a couple of weeks ago I was getting sent through, and our cells are battling against each other to, compete against, and then to create skin. To then, the dead cells falling away. We're creating waste. We're overheating. We're underheating, and all this kind of continuous battle to kind of survive. But it's that kind of battling, but cooperation as well.
We did want to talk about penguins, and I don't want to deny our viewers that nice video. We do have a question from the audience that from the website that it does seem to relate directly to insects, and the question is, how important is it to take a look into ants, bees and other insects to get bio-inspired algorithms? Could it have a big impact on the way we design cities? Which I guess you've kind of talked about a bit, but I don't know if you want to just hammer home that point a little more.
Yes, I would say. There's going to be a research paper published by UCL in the next couple of weeks after a 2-year study looking at kind of complexity and the study of swarms, because we can start understanding how basically building in behaviour as well, and understanding kind of the randomness of what are a supposed randomness of these systems. Because if you think about it, if you ever walk around and just walk around shopping centres and watch how people randomly, walk around, either they're walking meandering or have a purpose, we can actually start learning from them.
Cool.
Because if you think about the insects as bees as well, you're not just then on the horizontal plane, you've got the vertical as well, so you can start thinking about up in the air and how they navigate through a 3D sphere.
So penguins. What's so interesting about penguins?
They taste quite nice. I like the chocolate on top. Are we not talking about that? No.
they provide an interesting platform to drink tea through.
An interesting platform to drink tea through.
Yes.
Are you talking about the biscuits? Are you talking about the...
Yes.
I'm worried about the thinking of what you're doing with the penguin and as RSPCA.
Are you guys saying that a penguin chocolate bar has been inspired by nature in some way?
No, we're just joking.
No, we're just messing about. So penguin coats are incredible examples of multifunctional protective systems. A penguin, when it's out on land, it's normally very, very cold, and they have various behavioural systems in place where they huddle together to keep warm, but they also have highly insulating coats that are very, very warm. But because these coats have air trapped in them in order to keep them warm, which is sort of what we talked about earlier, in order for the penguin to get access to food, they have to dive into really deep waters, sometimes up to 250 metres. And so having lots of air in their garment, in their surroundings, in their coats, isn't great because it creates buoyancy and would make it more difficult for the penguin to dive. So what they've done is they've evolved an amazing system where their coat switches from being a high insulator to a water-resistant barrier. And the mechanism, the way that works is down to the design of and the structure of the penguin feather. And I can
This is our most challenging sample.
Okay, I'm going to hold this one.
This is an actual penguin feather.
Yes, it is an actual penguin feather that I collected myself from London Zoo because they kindly let me into the penguin enclosure after they'd molted, and they were very grumpy, so they were happy for somebody else to go in there. So I'm not sure what you can see, but
describe it to us as well, just in case.
At the tip, so this is the feather from the side view. Okay, you've got this fluffy bit here is called the after feather, and this is what really traps the air and keeps the feather warm, keeps the penguin warm. And then you have the sort of main feather here, which is a slippy, kind of very slick surface structure. So going back here, if you look at the bottom, the tip of the feather here, this is the bit that goes into the skin. There's a little V here, a little bit of tissue here that's bent over. So there's a muscle in the skin that contracts when the penguin is outside of the water on dry land, and it keeps the feather upright. And then when it wants to dive into the water, it releases, and as a result, the feather changes its orientation in relation to the skin. So it compresses down like this and pushes some of the air out, but not all of the air. So not all of the air is pushed out, but a lot of it is, and then the rest of it gets pushed out via the pressure of the water on the coat of the animal as it dives through. You were telling me quite an interesting theory about the emperor penguins earlier, weren't you?
Yes, there's a theory about the fact that the emperor penguins, because they're larger, they actually, just before they're coming out of the water, they actually shiver and release more of the bubbles from next to their skin, and that basically creates, a bit like the golf ball, creates micro, basically, bubbles round about the, that's a bit different, round the penguin, and actually reduces the drag, so now actually have to use more energy to get out the water, but it allows it then to pop up and land in BBC cameramen.
So what essentially is a very simple system of a feather changing its orientation in relation to the body. It can control how much air and thus how insulating the particular the coat is. But it's not totally efficient. All the air doesn't come out of the coat before the penguin jumps in the water. And there is a function. This is a theory, and it's not 100% proven scientifically. There's scientists in Cork University looking at this. But the theory is that there's the air that's still trapped within the system, within the coat. As the penguin dives in, this air passes through the sort of little bits of feather and the after feather, and creates these tiny microbubbles that alter the nature of the water right as the penguin is diving through it. So it actually reduces the friction, and it's less dense, the water right next to the body. So they have the ability to alter the nature of the material around them.
It's a complex problem, and that's one of the interesting things. A lot of the modern design briefs are, it needs to be able to do this, and this, and this, and, you know, penguins are doing this, and this, and this. We're going to play a game, because we've been promised that you are biomimicry experts. We want to test that live for our live audience, how inspired by nature you can be. There's one quick question I wanted to ask, because there's going to be people in the audience, and it's not scored, although it can still be competitive. One quick question maybe for the audience may be thinking right now. You know, we have a lot of young designers who watch the diff. There may be, I mean, some of this seems quite scientific, seems quite complex and technical. How do they get involved? How do they start? Should they feel intimidated by the challenge, or, you know, what are some of the beginning points, I guess? What's step one?
Step one is befriend a biologist and teach them, and they will teach you how to read a research paper. I mean, over a long period of time, I used to give undergrad product designers biology papers, and I then had to clean up the mess as their head exploded, because there's very, very little information they really need to know. They just need to know what are the problems solved by that particular species, and it's literally, it could be a sentence or a paragraph. It could be entering design challenges, or literally exploring and reverse engineering products that are already been designed.
Step 0, I would say, is to be curious. You need to be curious, you need to be able to have that, but also be creative and encourage that creative thinking and looking, and, you know, can you abstract and relate things, you know, you sort of look at something and say, oh, this is similar to a fabric, for example, and then make those links. But I think curiosity is really the first step.
Yeah, an example being outside, we were talking before we came on air, and Veronika's products could be used in the building industry as well. You know, I've got another business, my co-directors are interested as well, using the fabric for horse blankets. So it's looking at how many different areas and that it can be used in, and just be creative, because you never know where a product, for example, in the motor trade could be used in healthcare, because it's a product that's been developed and might actually better applications, and you're not quite. So it's meeting not only the biologist, but also an entrepreneur. If you're an inventor, you need to meet an entrepreneur who knows how to look to different markets as well.
I like those two. So 2 tips: kind of be curious and be open to biology. And I guess the one challenge with the biology piece is that biologists, I guess, are not really writing their papers to inspire product designers, because that's just not incentivized in their field. Do you have any have you got a biologist friend, Richard? Is that how you got started in this, or what's
We have someone in common, haven't we?
Yeah,
are you allowed to divulge?
Yeah, it's Julian Benson, and then also one of my freelancers is a general biologist as well. So you need a specialist, but you also need a generalist who knows more than the left wing of a butterfly. He knows about the ecosystems, he knows about lots of different areas, and then he can bring it all together, so he can help you spread your wings. That's a bit of a metaphor there, to go out and find the things you need to, because it is hard, because where do you start off in the tree of life? Do you look at bacteria all the way up to the kind of the superorganisms of the giant redwoods and blue whales? Where do you start? Because there's lots and lots of convergent solutions in there. And it's tapping into being strategic and finding the right one, instead of having kind of eureka moments like George DeMestro had with Velcro.
We talk a lot in the circular economy about the value of being able to zoom in and then be able to zoom out. Kind of Ken Webster calls it the macroscope. That's a coin from Joel de Rosny, system thinker. The ability to like have that really tight perspective, the buds, but also the big systems perspective as well. Anyway, so there's your tips. We do have one more topic we have to cover, which again is coming through in some of the audience questions, which is, how do we scale this and what's the impact? But before we go into those serious matters, I'm going to press this button, and I'm not 100% sure what's going to happen. So,
from an eel to a bear to a cockatoo, which animals inspire you? Meow.
So, this is the inaugural diff, which animals inspire you game. And so what I'm going to do is I'm going to show an image of an animal. And what I just want you to react off the cuff. How does that inspire you? What can you imagine being created off the back of it? So hopefully the first one's an easy-ish one. Butterfly. Everyone loves a butterfly.
Oh, you've got structural colour there. So the blue's not blue, it's brown.
Okay.
So there we go. So you've got...
How is that blue-brown?
Because it's the way that the light's actually reflecting through these little tiny... They're effectively like little Christmas trees, aren't they? And you've got applications, so General Electric are looking into improving for thermal imaging cameras. You've got a paint Lexus on their car called the Blue Morpho paint in the car. And various other applications, even into textiles as well.
Funny, I'm the textiles person, but I'm thinking of lightweight flying structures.
So the fact is, some butterflies, of course, some butterflies make huge. One butterfly makes a huge, make a huge migration, and yet they're these tiny little things.
So that's 1-0, Richard. Well done. Yeah.
Yes, that was actually very, very good, very impressive. Obviously not challenging enough, so we're going to take it up a slightly tougher level, hopefully.
I'll give you that one.
Oh, you're a grunt.
This animal, is it clear what it is to you, just to check that we're familiar with this creature? It's, of course, an anteater.
Yes.
Posing.
Yeah.
Not what the ants on one of our previous videos want to see, obviously.
But possibly where they end up.
Certainly got a long tongue. That's something I always think about with an anteater.
Yeah, I'm thinking an interesting hoovering system.
Hoover.
Ways of reaching, it could be tips of injection devices when you want to deploy different materials or different substances. Its snout has a really interesting sort of, I wouldn't quite say aerodynamic quality, but Richard, go on.
Yes, how far can you throw an anteater? That's the question that comes up time and time again. No, I was thinking as well, so you're not just looking at the mechanical structure of the tongue, you're looking at actually down to how's it actually, what the functions are there, what's the direction.
It must be quite sticky to be able to capture ants.
And then so that it's going back into the head.
They've got these little hooks on their tongues, which is, I think, common to the penguins have them as well. All sorts of animals that rely on their tongues to grip their food, and they don't have claws or a way of catching them.
See, this game might seem playful, but it's actually really demonstrating to anyone watching at home that's the two things you're kind of saying: curiosity and having a little investigation into biology.
But even look,
hello. Oh, I've given away.
I was even thinking down to the fur as well. I mean, it's a changing densities. It's back.
Very fluffy tail, for example,
which could be down. It could be a cooling system. I've been thinking about. You've got. They're going to get bitten a lot, aren't they, by the termites and ants that they're actually eating, or if they've got any properties in their blood that are minimising if they're actually getting attacked by, animals that do inject poisons as well.
It would be unfortunate if you were an anteater who's allergic to ant bites, wouldn't it?
It would be. You wouldn't be, yeah.
So the next one of my favourite animals, the common slug.
I think the patterning on its body would have some
quite a nice photo, actually, isn't it?
It is, yeah. It would have some very interesting properties in terms of repelling particular or resistance to impact. I think they produce a bit of slime as well, so that idea of coating yourself in something, a structure in something to enable it to sort of move, and then that structure being biodegradable, or that coating being biodegradable and disposable.
So our hypothesis is the slime, because I've noticed that when it rains, slugs come out and they just leave these trails of slime, and I've always thought to myself, why? Well, actually, I'm thinking it more than I've previously thought it, but why do slugs leave slime all over my garden when they, you know, what's the use of that?
Well, it's easier for them to move around. And then, so you're, I mean, another application could be soft robotics, getting into small, tight spaces.
Yeah, because the muscles in their bodies that are responsible for the contraction and the of the body and sort of it as essentially moving around are really interesting, and they do have applications in soft robotics. You can, I think there's quite a bit of work around, you know, creating robots that sort of crawl and slide along like slugs.
Yeah, I mean, obviously the downside, you wouldn't create a soft robot based on a slug, but you could go to the military applications, just go around with salt and stop them.
I was going to say, slug-inspired robotics, that sounds actually like it could be quite catchy. If anyone wants to steal that idea, I don't have time to pursue it.
Or make a jingle out of it.
Yeah. So, final one, tiebreaker. Well,
I'm winning,
We've had four, so it's not really a tiebreaker, but... Do we know what this is? I'm trying to remember myself right now. No. This is a blobfish.
A blobfish.
Bad night out in Newcastle. No.
Blobfish.
So they're living very, you know,
close together.
Yeah, down deep in the ocean. Where did you get these pictures from? So you're looking at how they deal with pressures deep in the deep ocean as well. You know, how are they seeing as well? Because obviously they've got big eyes, but are they actually useful? I'm sure they're probably predators as well, so how they're catching the food.
Is that based on the fact that anything you've seen there that makes you think they're a predator, or just like a...
I don't... They look more like bottom feeders, don't they? Maybe they're predators. I don't know enough about them. We'd need to ask.
They've got very big heads.
They do. But
why would it be valuable to have big eyes if you're like in the... For example, I think blobfish do live quite deep down in the dark. Is that one of these quirks in nature where, you know, the obvious thing isn't so obvious? Well,
it's about capturing light, the minimum amount of light that does get through, and actually being able to then use that to either spot prey or spot predators. I mean, you guys have Michael Pullen a lot in his biomimetic office, employs that with the spookfish to actually bounce light into the atrium instead of using lots and lots of you know, electrical lighting.
So a blobfish inspired lighting system.
Or yeah, optics or something like that as well.
Well, there you go. That's the end of... You can score that however you want, but that's the end of the first What Inspires You, What Animals Inspire You game. Feels like... I mean, we have got a couple of questions in from the audience that kind of speak to this, from Scarlett and Freya. They both kind of asked a similar thing, and I think it's a reasonable question to ask, which is, you know, what does scale look like for this? How do we actually... Because I guess the implication is that most things are not designed in this way, but maybe most things should be designed in this way. So what's the path from most things not being designed in this way to most things being designed in this way?
Well, there's got to be an industry need. And you've also got to prove it can work as well. I mean, the biggest challenge, for example, looking into biomaterials and the fact that, you know, there's biological composites out there that actually solve the problem, same as 300 or 600 of different man-made ones, is actually getting them to have the same, you know, life cycle and not degrade. You've also got to meet the right people who can actually help you really develop a serious, very, very strong business plan, and then put you in front of the right investors. Because, I mean, you know, Veronica's talked a lot about her stuff, you know, taking 10 years, and it's not just, you know, biomimicry and biomimetic examples of that. You're talking standard things in industry. You know, looking at the golf ball. I mean, yes, it's just a golf ball, but think about the, you know, cover up the manufacture of it, but how many years investment into a golf ball and the different ranges, and every time they release one, they'll have another 10 that they're going to think of the next year and the next year, and continual evolution of their process.
And it's also from a completely different perspective. You know, with my experience in actually developing a technology and going through the processes of scaling it up. In the textile sector, and the textile sector is hugely conservative. There's huge bits of equipment that cost millions and millions and millions, and you know, they're sort of set up to do very specific tasks. And there comes somebody like myself along saying, okay, I want you to process fibres that change shape. Now, the fibres that, we sort of give to our various industry partners are the same size, the same width. We even use commercial polymers, but because they change shape, it completely, technicians that work with us have to throw the rule book out the window when it comes to processing them, because the entire industry is set up around fibres to not change shape. They want them to stay the way they are, so then the final product is the length that they expect it to be, the width that they expect it to be, to have the dimensional stability. So this is a major nightmare. This is a textile technologist's nightmare. But we've had to work with industry partners and conduct R&D in order to develop new ways of understanding and designing with materials that are dynamic and change shape. And I think that will, as more and more ideas and innovations happen, I think that slight modifications to existing production systems is one way forward, but then you've got these completely disruptive technologies like 3D printing and additive manufacturing, which enables you to have a lot more freedom in the production process. But so there's not one answer, there's lots of different...
There's one thing to say, I've got a solution, I can prove it works. It's another thing to get the industry to adopt it. But we haven't talked a lot about technologies and kind of the opportunities that technologies provide. That feels like a sort of potential combination step change because it allows us to manage complexity much better with additive manufacturing, with AI technologies. Is that a key opportunity for biomimicry designers or people in that space?
Oh, you definitely. I mean, if you say the fourth industrial revolution or Industry 4.0, and that's a combination of the biological, the cyber, and the physical systems all interacting. So what if you could use ants to construct your house? They don't have a union either, so they'd be working all the time. But that's that kind of thing, is learning from those natural systems to help all combining and working together. So you could use natural systems as part of the filtration part of your house, or more in your city systems as well. And you're seeing that a lot more countries are developing that along with sustainable manufacturing, because as Veronika just mentioned, you have to think, are we inventing the new product, or should we be looking at the new manufacturing process? Because that could be where the bigger game changers coming out there, because if we can minimize the energy usage, or the water pollution, a little thing, instead of then focusing on, I have to design the big shiny new product all the time, because it might just be you create this amazing product, but it can't get manufactured because nobody has the facilities out there.
Maybe a final question from me is this inevitable? Is it inevitable that we're going to be designing more and more with biomimicry inspired design, or does it need a push from somewhere? Does it need certain people to be driving it forward in certain ways to to put it even more firmly on the agenda?
Yes, because we need to understand nature more. It's very complex. We're still finding out. It's even hard to define what life is, and we need more and more analytical tools that can give us systematic ways to create new products and services. And you're seeing that with Ask Nature. I'm lucky enough to be on their advisory board, and they're looking at more ways to actually engage with people to understand biology. You've got other products like from Georgia Tech, or the stuff that Julian Vincent's doing about really showing people this is how nature works, and this is a solution space to actually get into, instead of just randomly having to, find a seashell and then create something from it. You can actually take that seashell, understand how it works, and that might give you another 10 or 20 biological strategies that allows you to actually create something useful.
Building tools that people can use.
Yeah, and ideally, in the distant future, nobody will remember the word biomimicry, but that particular toolkit will exist within our normal everyday practice of design.
Designing the field.
Yeah, it's a bit like human-centered design and design thinking. It's getting more and more just common sense. People are thinking about you design for the consumer, the person going to use it, instead of just creating a product that you think it's functionally working.
Richard and Veronika, thank you so much for everything you've brought, all the tricks and the exhibition. It's been great. And thank you so much to you at home for the questions you've asked, for the comments you posted. And if you are a young designer out there, be curious. look at the natural world around you, and learn about recent biology papers as well. It's been a great session. Thanks so much for joining us. This is day 2 of a 5-day event. Lots more to catch up on at the DIF website. So make sure you go to thinkdiff.co, check out the Ellen MacArthur Foundation's YouTube channel, and we hope to see you again soon at the DIF.
We need to start making more conscious material choices.
Set up an initiative called Make Fashion Circular.
It's a tsunami of change.